let's start. So today I hope you have gone through the lectures by Professor Ram for the week 2 content and you have attempted the assignment 1. Uh, if you have any doubt in the assignment 1 or in the course content of the week 1, we can discuss at the end of this lecture. And during the lecture, if you face any doubt, any problem, just raise your hand or unmute yourself and speak. Okay, so let's start the first problem. So the first problem says determine the transfer function, poles and zeros of the system, and steady state value of the step response. There are quite a few terms here I would like to introduce and explain. First is transfer function. Second is poles and zeros of a system. And third is the step response and steady state value. So you might be knowing what a transfer function is, might not be knowing, but I would like you to visualize and get the feel what a transfer function is. So let's discuss what a transfer function is. So the transfer function, as the name suggests, it transfers. Okay, the transfer function transfers something. Let's forget about you are studying some control system and all. Transfer function transfers something. So if this, one second. So if this is my system, system. So I don't know what is my system, whether it's a linear system, it's a linear and time invariant LTI system, it's a non-linear system, it's some aerospace like aircraft, some plant. I don't know. I just know I have a system like a black box kind of thing. I have some input channel to it and some output channel to it. I can measure the input and I can measure the output. Okay. Let's assume I give some five as input, so 5 units, some any like current voltage or anything. Just take 5 units as the input, and I get 12 units as the output. Okay, can you say what the system is? Like it can be anything. Like if you take u is equal to 5 and y is equal to 12, so y can be 2u plus 2, y can be 2.4u, y can be 3u minus 3, y can also be 5 plus 7, sorry, u plus 7. Okay, everything satisfies this. So but any system has the property satisfying only one equation. Like it won't be like for a particular input it will be having some, it will be satisfying some like this equation, and for another input it will be satisfying some other equation. No, it doesn't happen like that. The system will be satisfying for all the inputs. Okay, so how to figure out, like what is the system, like what can be the system? Anyone can would like to join the discussion, like how to determine how uh, the system probably, like which one of the equations is the system equation? Yeah, very good, thank you, Saurabh. So what I will do, I'll give another input, u is equal to 10, then I'll be getting the output y. So what's the y? Just assume if it's 22. Okay. So then when I check which equations are being satisfied, I can see this equation is being satisfied. Okay. And the rest of the equation are not being satisfied. So can I be sure, like the system equation satisfies y is equal to 2u plus 2? No, because there might be some other property, like same, just by two inputs I cannot like define it. Okay. So okay, just a question, who have attended the last class. Y is equal to 2u plus 2. Is it a linear system or not? Is it? Can I see some chat in the chat box? Can somebody reply? Is it a linear system or not? like the graph is like y and this is u. It will be something like this. Okay, Saurabh says it's a linear system. Anybody else? Like like you should guess like whether you will be correct or not, but you should guess. So Saurabh says it's a linear system. So anyone else? It's okay. Balaji says it's not a linear system. I guess Saurabh, you have not attended the first week course. Okay. Okay, it's okay. Like we will be discussing same. We will be discussing the same problem statements. I have talked to him. Okay. So I would like you to know this. This is not a linear system. This is a linear curve, linear plot, but it's not a linear system. I will just briefly recap for who have not joined last session. So for a linear system to satisfy, there are two properties. One is homogeneous and another is superposition. Okay. If any of the property is not satisfied, it's not a it's not a linear system. So if I take y is equal to mx plus c, so and during according to homogeneous property, if I give the input y is equal to ax, some ax plus c, then my y dash will be this. This will be amx plus c. But for the linear system to be satisfied, it should have a into y, which is amx plus ac. I have c now, but I should have ac. That's why it's not a linear system. The curve looks linear, but it's not a linear system unless c is equal to 0. So for any system to be linear time invariant or a linear system, the system should pass through origin. It's a very tricky question. Sometimes you get this kind of questions in your gate exam or some interview or in like higher studies also. It's a very tricky question. That's why I wanted to highlight. Is is this clear to everybody? Then I will go forward to transfer function. Can I see some yes or no in the chat? Okay. Thank you, sir. Anybody else? Like, okay, cool. Then, yeah, our discussion, today's discussion is transfer function. So what's a transfer function is? So as I have mentioned here, like a system takes some input, gives some output. So transfer function defines how the system's transfer function will determine what the output will be. In simple language, transfer function, sorry, in simple language, transfer function defines the relationship between input and output. Okay, so it's not a book definition. If in exams it comes the what is the definition of transfer function, you should not write this. You should write the book definition. This is just a overview. You should get what it does. Okay, so okay, now this is the transfer function. So this if I have a system, I give some input u of t, I get some output y of t, then the y of t by u of t will be my transfer function system, like the transfer function. And if we take the Laplace transform, the y of s divided by u of s will be my transfer function of the system in Laplace domain or S domain. So in the last class, we have discussed why we should go to Laplace domain. Like we know, in control system, you might be knowing everybody goes to Laplace system, from a continuous time system we jump to Laplace system. We do the Laplace transformation. But why we do? That's discussed in the last class. Okay. So now the transfer function we know. Then what happens? Okay. Now come back. Let's come back to the problem. The question. The question, it's given uh, y double dot of t plus 6y dot of t plus 5y of t is equal to u of t. Let's forget what the input is. Like, transfer function is independent of the input. Here as I have shown in the diagram, the transfer function of the system is independent of what input I am giving. The system has its own transfer function. You give some input, you get some output. Okay, so it's independent of the input. So forget about what's the input. Whenever you are getting the transfer function, you should not worry about what is the u of t. Okay, so that let's take the Laplace transform of both sides. So it will be, and another important thing is the input conditions, whatever the initial input in initial conditions should be 0, so that the Laplace transform will be s square y of s plus 6s y of s plus 5 y of s is equal to u of s. Then I can write my y of s divided by u of s is equal to 1 by s square plus 6s plus 5. This is my transfer function. Correct? Anybody has any doubt in this? Okay, cool. So we have derived the transfer function. Now comes the poles and zeros of the system. So how many of you have heard the terms poles and zeros? You might, like, all, I guess all of you have heard the terms poles and zeros uh, anywhere, but I want to know how many of you know what it does, why we are studying about the poles and zeros, why they are necessary. Okay, so I'll brief recap kind of thing. When we go from a time domain, this is a continuous time, like f of t is a function in time domain. The independent variable here, t, is in time domain, defines the time. So when we go this to the Laplace transformation, after Laplace transform, the S domain, where the axis becomes real and imaginary. Okay, when we transform using the Laplace transform of f of t gives f of s. We convert our continuous time domain signal to a frequency domain signal. So s is equal to a plus jb. Let's assume, okay, generally we take alpha plus j omega. I will take that alpha plus j omega. So a continuous time domain signal is being thrown into a frequency domain signal. How these conversion are done, we'll be knowing in the latter half of the course. So for now, just remember this. Okay. So what the pole and zeros do is, like, when I have a system like this is my system. When I give, now I am in the, I will write, I am in the frequency domain. Like, that means I am in the Laplace domain. Okay. When I am in the Laplace domain, I will be giving the input as a frequency only. So some frequency may be a plus uh, bj omega. Okay. If I give this as my S1, okay, and how my system performs, I will be getting some output, any output. For what value of S, I will be getting zero output, totally nil output. That is called zero of the system. And for what value I will be getting amplified, like much amplified, like infinite kind of output, that is called the pole of the system. You know, the, like, from the denominator and numerator, if we equate denominator to 0, you will be getting the zeros, and denominator to 0, you will be getting pole. Just think about in the while designing a like band pass filter or some filters, some low pass filters or high pass filters. Okay, this is not regarding this course. I want to give you the feel of what poles and zeros are, because poles and zeros will be coming to you frequently in this course, so you get the idea like what they are, why they are useful. Because when I was studying during my bachelor's, nobody had taught me like why poles and zeros are important. So just imagine I tell you to design a system, any system that will amplify particular 10 kilohertz signal, and it will reduce, it will like it will reduce like the it will attenuate, it will attenuate whatever 5 kilohertz signals are there. It's in the frequency domain, a normal filter. You can try using different methods. Your basic plan, what you will do, I want to amplify here and I want to attenuate here. So in this real and imaginary plot, if you put a 0 at 5 kilohertz, a 0 at 5 kilohertz and a pole at 10 kilohertz, then definitely you will see when a signal comes at 5 kilohertz, because the system has a 0 at 5 kilohertz, it will be going down, it will be attenuated. Like if the signal is coming, if it's 5 kilohertz, then it will be attenuated. As the pole is at 10 kilohertz, it will be amplified. The poles and zeros are very useful when designing a system. You want your system to behave like this, like you want your system like your, my working range, working range in the frequency domain is 2 to 3 kilohertz. So rest of all the signals are noise and you want to attenuate them, then you can add the zeros there and the poles over there. Is it clear why poles and zeros are important? Because the questions you will be getting in gate or in your exams, find the poles and zeros at this value, find your poles and zeros at that value. It will be very simple. But this concept, like why poles and zeros are important, that's a bit tricky. Okay, am I clear? Should I proceed to the question? Okay, thank you, Saurabh. So coming back to the question now, I have my transfer function here. So what are the poles and zeros of the transfer function? Can I get the answers? This transfer function, what are the poles and what are the zeros? Uh, in the chat box, can somebody type the answers? Sir, could you please repeat the application of the after the problem? Yes, Balaji, definitely. The application of poles. Okay, Saurabh says the poles at -1 and -5 and 0, none. Very good, Saurabh. It's the correct answer. You can get here in the numerator only 1 is there. So if you equate 1 is equal to 0, that's not valid. So if you in the denominator s square plus 6s plus 5 is equal to 0, you will be getting s plus 5 into s plus 1 is equal to 0. So equating them, you will be getting -1 and -1. Very good. Now comes the steady state value of the input response of the system. So can somebody say for the unit step response, what's the Laplace transform? I have discussed in the last class. So can anybody type in the chat what's the Laplace transform? Laplace transform of unit step U of S. Okay, Balaji and Vidyadhar and Saurabh. Yeah, it's 1 by S. So when I'm And remember, it's a trick in the question. Whenever you see in the question this term, response. So response means most of the time, unless it's specified, it's time domain response. What's the response in the time domain? Okay. And what's the output behavior? That means what you need is y of t. Okay. So two things you can do. You can double integrate the equation, but I won't recommend it because it will be very hectic and it's hard to solve. So we have y of s. That means y of s is equal to 1 by s into, sorry, I will just write everything, is equal to u of s into transfer function. That means 1 by s into 1 by s square plus 6s plus 5 is equal, that's the y of s. Okay. So two things we can do. I will give you a trick kind of thing, and other thing is what you can do is y of t. You can take the inverse Laplace transform. For before that, you need to do the partial fraction. In the last class, I have discussed y of s is equal to 1 by s into s square plus 6s plus 5. So you can divide it into a by s plus bs plus c divided by s square plus 5 6s plus 5. Okay, and get the values for a, b, and c, and then convert it to y of t, whatever the inverse Laplace transform from y of s. That's a bit tedious process. That's a longer problem statement. But I will give you a trick kind of thing which is applicable to this kind of problem statements where only the steady state value for a unit step is required. Whenever you see a steady state value, what does a steady state value mean? Can somebody type in the chat like what do they know about? What do you mean by a steady state value? Hmm. What's the steady state value? Can somebody just say? Okay. Balaji says it's t is equal to 0. Uh, Samartha says it's the final value. Samartha, can you explain what do you mean by the final value? If it's the sinusoidal in sinusoid, okay. Mm, like t, this is sine t. So what's the final value? Uh, Final value in for a sinusoid. Okay, final value at t is equal to infinity. That is correct. But can you say what's the final value of uh, sine t? Because you have mentioned a very good term which I will be explaining now. Final value. Balaji, you need to recheck it. For the steady state, it's not t is equal to 0. It's t is equal to infinity. Okay, like when my system is settled, like okay, okay. For a sinusoid, we can't define the final value. Okay, because it's variable. It can be having anything in between -1 and 1. Okay, final value are generally defined for system. They are converged to some value. They converge to some value, then I can say what's the final value, what's the steady state value, where it's not, the value is not changing. That means the value at t is equal, t tends to infinite. Okay. So whenever you see the problem where it's mentioned steady state value, then you can apply, okay, initial and value. Okay, you thought, okay, no, initial value and final value are different. So whenever you see a steady state value, you should apply a final value theorem. Okay, what's the final value theorem? It's very important. Whenever you see steady state response, steady state value, your first thing that should come to your mind is oh my god, final value theorem. Okay, what final value theorem says is, if I have some y of s in the Laplace domain and I want the steady state. Mark my word, I am repeating the words again and again so that you shouldn't forget it. it's only applicable when the steady state value is required. That means when t tends to infinite, then what I can do, the y of t tends to infinite will be limit s tends to 0 s y of s. If you have some pen, paper, something, just write this equation and remember it. The derivation I can do, but that will take a lot of time. I don't want to go into that. But this is very important theorem, because by this step you will be solving the problems like I don't know how to do the chutki, but you understand this. So the problem which we had used to take so long time. If you not use the normal procedure, it will take hell lot of time. But now, just let's apply the final value theorem. I will use some other color, green maybe. So this is my transfer function y of s is equal to u of s, like at t tends to infinite, y, like y of t. This is y of t s. So limit s tends to 0, okay, s y of s. That means, can I get the value? What you will get? 1 by, like, s into 1 by s. So it's get s square plus 6s plus 5. Can I get the value from someone? Any one of you? What is the value? Steady state value? Or I can write here. Y of t at t tends to infinite. Okay, let's check. Uh, Balkiran says 1 by 5, Saurabh says 1 by 5, Vidyadhar says 1 by 5. Absolutely. It's simple. S tends to 0, 1 by s square plus 6s plus 5. So just put s is equal to 0, you will get 1 by 5. Correct answer, you will be getting 5 out of 5 marks in this question. Correct. Should I go to the next problem? Everybody is clear about this problem? How to approach and all? Yeah. Thank you. Okay. So the next problem is find the system response to the given input under 0 initial conditions. So few words, if you have heard me correctly, whenever it's written system response, that means you need to calculate y of t. Okay, correct? System response, how the system responds to an input. I have given some input, and the input is given y is equal to, sorry, u is equal to sine root 2 root 3t, and what is my system response? So I want the answer in time domain, not in Laplace domain or frequency domain. Okay, so let's answer this question. It's very simple, but if you have pen and paper, start solving it. Okay, first somebody, like, just type, if it's the sine at. Okay, what's the Laplace transform of sine at? In the last class I have discussed and I have given a trick to remember that. So can somebody type in the chat what's the Laplace transform of sine at? uh, is Tommy here? Yeah, Tom, last time you had made a mistake in the sine and cos Laplace transform. So if you remember, can I get an answer from you this time? uh, okay, Balaji says 3. Okay, he has taken the example. Balaji says Balaji 3 by s square plus 3. Okay, anybody else? Can I get, like, I can get, like, you can write from for at or root 3t, anything. uh, I'll wait for a couple of more seconds. Okay, okay, uh, Saurabh says it's s by s square plus a square. Okay, John, okay, John says it's a by s square plus a square. Yeah, Saurabh, you need to recall I had mentioned for cos ends with s. So let's start with s. So then the nominator has s. For sine, uh, it's just the a by s square plus a square. Okay, and Balaji here the a is root 3, not 3. So you need to careful. Your answer should have been root 3 by s square plus 3 instead of 3 by s square plus 3. Okay, you need to careful. These small mistakes will take a lot of points out of your hands. Okay, so let's get back to the question now. I'll remove these things. So the question is, okay, let's do the Laplace transform. If you have pen and paper, do it parallelly. Okay, it's s square y of s plus 3 s y of s is equal to root 3 by s square plus 3. And this term, never neglect this term under zero initial conditions, because that is why the y double dot t has this Laplace transform. Otherwise, it would be having some other terms as well. So let's not go deep into that. Okay, so let's solve the problem. What's the y of s? Y of s is equal to root 3 divided by s square plus 3 into 1 by s square plus 3. Sorry, 3s. So can I, okay, now it's root 3 divided by s square plus 3 into s into s plus 3. I am making it simplified. So can I get an answer? So let's see who are active in the class now. So if I do some partial fraction, I have mentioned in the last class, a by s plus b by s plus 3 plus cs plus d by s square plus 3. Can somebody confirm the values? What are the a, b, c, d? Because I have calculated the answers, I have my values, but I want you guys to be participating in this. So can I get the values of A, B, C, and D? I'll be waiting for 2 minutes. Okay, I get an answer from Balaji. So Balaji says A is equal to, okay, I'll use some other color. A is equal to 1 by 9. Balaji, just check. I want you to just recheck if you are not missing the root 3. Okay, just be careful. Today you are becoming little bit rusty, because in the nominator it's not 1, it's root 3. So be careful and recheck your answer. Okay, so if you have done or not, but I'll proceed with the lecture. So I will write the answers. You can just recheck it. A will be root 3 by 9. B will be minus root 3 by 36. C will be minus root 3 by 12. And D will be minus root 3 by 12. Okay. Uh, three. Okay, you can, Balkiran, you can just recheck these values. I have calculated these values, so you can check. Okay, so let's proceed. Like what I want my y of t, but I have y of s, so I can do the inverse Laplace transform. So what I have got is y of s is equal to root 3 by 9 into 1 by s plus minus, sorry, I should write it minus root 3 by 36 into 1 by s plus 3 uh, minus root 3 by 12 into s plus 1 whole divided by s square plus 3. 3. Okay, so what happens if you do the inverse Laplace transform? So you can verify it because it will take time. So I'll just write it down. So the answer will be root 3 whole into 1 by 9 minus 1 by 36 e to the power minus 3t minus 1 by 12 cos root 3t minus 1 by 12 root 3 sine root 3t. It will take quite good amount of time, 10-15 minutes to solve this problem. So you need to calculate. So this kind of problem will be generally having in your colleges. If this kind of problems appear, they will be having 5 to 7 marks maybe. So be careful about the solution. And now the tricky part. If I had mentioned the response, steady state response or value, whatever the spelling. Okay, so steady state response, then you could have easily calculated s tends to 0 as y of s. The what's it's called? Yes, you are right. It's called the final value theorem. This problem is clear, everybody. Should I go to the next problem? Okay. Okay. This is the problem. Like comment on the stability of the system whose governing equation is given as. This is a big equation. Don't be terrified by the equation. The concepts are simple. If the concept is clear, the solution is done. Okay, that's the basic principle. So before solving this problem, I would like to just brief you about what is stability in LTI system. These stabilities are no more valid for a non-linear system or time-varying system. So this term for a LTI system, it's very important. You must mention like the whole control system syllabus you will be learning in this semester, in this course. It will be okay. Ishan says, hello sir, can you explain again why you use the limit method only steady state? Yeah, sure. Okay, I will be mentioning that. So the stability in LTI system, because the nonlinear part is not covered in this syllabus, you will be encountering only LTI system. So there are two kinds of stability. One is Bibo stability and another is internal stability. Okay. So what the Bibo stability is, I have my system. I don't know what the system is. I don't care about the system. Okay. I give some input and I get some output. This is the basic principle, general principle of control system. I give some input to the system, I get some output. If I give the input bounded, my system has some limit value like upper limit and lower limit in between. If my output is also bounded, my output doesn't go beyond some value, then that's called the BIBOS. Bounded input, bounded output. The name itself is self-explanatory. But the internal stability means If the system, my system has its own some poles or poles that make the system unstable. Mark my word, internal stability is like one is, you might be knowing one term that is called the impulse response. Okay, when I am a designer, we all are engineers. Okay, what we want to design something to solve some problems. So when I am designing a control system or any system, what should be my first priority? My first priority is the system should be stable. It doesn't matter how good it behaves, how bad it behaves. If it's not stable, my system is worthless. Like it shouldn't be considered as a system. Okay. Okay. So my system should be first priority. When I'm designing something, that should be my first priority is the system should be stable. Then I will be analyzing the performances. The performances we will be learning in week 3 or week 4. Week 4. After the stable, is my system stable for a particular input or all the inputs? That should be my second concern. First, because I'll be having the system. Let's try with this input. If it's stable, yeah, I'm good. Let's try with another system, another input. So in frequency domain, what I can say, my system should be stable for all the frequencies, not just 10 kilohertz, 50 hertz, 5 megahertz. It should be stable for all the frequencies, starting from 1 hertz to 1000 hertz or any value, so that I can say my system is internally stable. Unless you, the input, who is the giving the input, you are making some problem, my output will be always be stable. There is nothing wrong with my system. Okay, so impulse response, the in the time domain, impulse response can be denoted as delta t, what's called. It's only at the time zero and a high value, the impulse. That's called the impulse. If we do the Fourier transform or the Laplace transform of this input, what's the Laplace transform of input? Sorry, impulse. Does anyone know what's the Laplace transform of impulse? Can I get some answer? No, Saurav, that is for 1 by s for unit step. That is, the plot is like before t is equal to 0, it's 0. After t is equal to 0, it's 1. This is unit step signal, because it's kind of a, you can see there is a step kind of at t is equal to 0. That's why it's called step. I'm talking about impulse signal, not unit step. There are two types of inputs. So at impulse, only at t is equal to 0, we have a large value. Just like somebody slaps you hard. For 1 second, you will be getting the slap. So, okay. Okay. So, okay, no plus or minus term. Okay, I'm giving the answer. It's 1. Okay. The Laplace transform of a impulse response is 1. So if we plot that in the Laplace transform in j omega, or the frequency, and then it's 1, whole 1. So that is why whenever we get a system, first thing we do is we do the impulse response, so that I can check if my my system is stable for all the frequencies or not, because the impulse response for Laplace transform covers all the frequencies, j omega. Okay, this is the j omega. This is in time domain. Same plot, it's in the frequency domain, and in the frequency domain you can see it covers all the j omegas, all the omegas. So when I'm designing a system, my priority is system should be stable, and it should be stable for all the frequencies. That's why we do the impulse response. So there comes the internal stability. Okay, It's just the introduction. You won't get this insight in any book. Okay, this is only you can get from the lectures, video lectures of Oppenheimer, available in YouTube, or Professor M. Gopal, okay, of control system. Okay, next coming to the question. Okay, no, I would like to say few more few more things. So now I know my system should be internally stable. Like my system, if this is my system should be stable, internally stable. So what if my system had some poles? Then my system transfer function is like A by S plus B. Okay. Then what happens when my S, which is a frequency kind of thing, I give minus B? What will happen if I give the input S is equal to minus B? Then the system will blow away. So, and my, okay, coming back to the question now. Okay. Uh, I hope that part is clear. My BIBO stability and internal stability, and why the impulse response is important, and stability, regarding stability. So one key feature, hmm, in the transfer function, write it down if you have pen, paper. Uh, in an LTI system, the transfer function should, oh, sorry, have all the poles on the left half of the plane, the S plane, I would write S plane, to be stable. Okay. Because can somebody say what's the time domain response, like inverse Laplace transform S A by S plus B? Can anybody just answer this? A by S plus B. What is the inverse Laplace transform in time domain? Like definitely the inverse Laplace transform will be in time domain. Can I get some answer? It's very simple. Okay. Samartha says A e to the power minus Vt. Absolutely correct. It's perfect answer. So now let's try to plot this. Okay. Because any mathematical equation, if you can visualize it, the the course becomes very friendly and useful. Like you'll enjoy the study. Okay. So let's try to plot. If it's time domain, so I'm getting t, and this is my y of t. So if let's, for time being, let's take a is equal to 1. If b is positive, and in some other color, uh, if b is negative, what happens? If b is positive, then the plot will be coming like this. And if b is negative, then the plot will be going like this. Sorry, pardon. Going like this. So b is positive and b is negative. Because if b is negative, then this whole term becomes like e to the power bt. This minus b becomes positive, so it will be diverging. That's why can I say the system is stable? Because as t tends to infinite, here when b is greater than 0, my system is tending to 0, whereas my for b is negative, it's going beyond. So whatever the value you get, if it is my like this s plus, for from the s plus b, we get s is equal to 0, s is equal to minus b. This should always be in the left half of the s plane. Otherwise, the system will be unstable. This is the only reason why you all the poles for the stable system, all the poles should be on the left half of the s plane. Am I clear? Okay. So now coming back to the question. Now coming back to the question, just do the Laplace transform. It's very simple. S fourth ys plus s cube 8s cube y of s plus 22 s square y of s plus 24 s y of s plus 9 y of s is equal to u of s. So the transfer function will be y of s divided by u of s is equal to 1 by s fourth plus 8s cube plus 22s square plus 24s plus 9. So the for the roots of the system, like the for the poles of the system to be in the left half of the plane, you need to calculate the poles of this system. It is hectic because it's a fourth order polynomial. Generally, in exams, you won't be getting this. I just took an random example to explain you guys. So, in general, in exams, you might get up to third order. So, for this, you need to calculate this equal to 0 and calculate. I'm just writing the solutions. The solution will be 1 by s plus 3 whole square into s plus 1 whole square. You can check it out. And so the poles, the system pole is at minus 3 and minus 1. Two poles at minus 3 and two poles at minus 1. So everything is on the left half side. Like they have negative real part. So they have the negative real part. That's why it's 0. Okay. So it's the stable system. Okay. Let's see in the chat. Vidyadhar says, can you explain again? Okay, which part, Vidyadhar? If I'm not mistaken, why it should be in the like negative half plane or the plots which I have drawn? You want to why pole should be on the left side? Okay, why pole should be on the left side? Is first thing, uh, 1 by s plus a. Let's try it out. Vidyadhar, I want you to be interactive during this. So, what is the pole of the system? Can I get quick answer from you? The pole. Okay. The pole is minus a. Okay. And can I get the inverse Laplace transform? That if it's y of s, the what will be the y of t? The time domain response. Okay. E to the power minus 80. Very good. So let's draw the s plane. This is real and this is imaginary. Okay. So if there are two conditions, if a is negative, if a is positive. If a is negative, so I will use some different color. So if a is negative, then it will be having the pole. The pole is on the right hand side. Is it clear? And if A is positive, the pole will be in the, sorry, some other color is in the left hand side. Is it clear, Vidyadhar? This is if A is negative and this is A is positive. Okay, so look at, let's try to plot this y of t. Okay, so if I plot this y of t, if A is positive, okay, A is positive, let's try to take some example. A is equal to 5 and A is equal to minus 5. Okay, when A is equal to 5, when A is positive, then my plot will be e to the power minus 5t. So you can plot it as this, e to the power minus 5t, exponential curve, simple. But if A is negative, so it will be e to the power plus 5t, then the plot will be this kind of. So as t tends to infinite, for A, for negative value, for A is positive, where this left hand side plane, the value tends to, then the value tends to 0. This plot tends to 0. So it's a stable system. But when A is negative, the pole lies in the right hand side of the plane, it blows away. So system is clearly unstable. Is it clear now, Vidyadhar? Okay. So, and I think we are almost done. So, any doubt? Okay. One doubt I remember in the initial part of the class, that was the application of poles and zeros, regarding the application of the poles and zeros. Uh, so what happens is, when we are talking in frequency domain, uh, and please answer please answer of the problem 2 again. Okay, I'll show you that the answer of the problem 2. One second. I'll explain this poles and zeros. Someone had asked in the frequency domain, like when we are, like what pole does. Pole does is, it, when the frequency matches with the pole, like S is equal to A, then S is equal to, when I put S, when my system is 1 by S plus A and S plus B plus, okay. So what happens is, when the for my I give some input A is equal to, I test the system at S is equal to minus A, at S is equal to minus A, or S is equal to B minus B. So this is my pole. My system, the output, whatever I'm getting the output, it becomes, it blown away. It becomes infinite. But when I'm putting S is equal to B, it becomes 0. So the application is when we are designing filters. So being an engineer, if you are, I say, design design a filter which will amplify 50 kilohertz signal and attenuate 2 kilohertz signal. Okay, then what will you do? You will just, in your pole diagram and in the system, you will put your pole at near 50 kilohertz, near 50 kilohertz, and 0 near 2 kilohertz, so that any signal that is close to 2 kilohertz will be attenuated, and any signal that is close to 50 hertz or 50 hertz, that will be amplified. Okay, is it clear? Some who had asked this question. See in the chat. Okay, Balaji, is it clear for you? And the final answer of the problem statement 2. Okay. The final answer A, B, C, D. You will get. Yeah, this is the final answer. This one. Okay, Ishan, I'll explain it now. One. Okay. Last term is 1 by minus 1 by root 3 sine root 3 t. Okay. So as Ishan asks, what is the final value theorem, steady state query? So as you know, what is the Ishan? I would like to ask you a question. What is the relation between time and frequency? Can you just type in the chat? What is the relation between? Okay, good. Time is inversely proportional to frequency. So when time tends to infinite, my frequency will tend to 0. Can I say this? Yes or no, Ishan? So when my time domain signal f of t, time domain signal t tends to infinite, I am the Laplace domain. Laplace is just a frequency domain. So by Laplace, I can say it will be s tends to 0. Is it correct? Okay. So whenever the problem says find the steady state value, the final value, these are the simple terms, steady state value, final response, then what you need to do is when the y of s is equal to, like the, I'll write it, for final value t tends to infinite, y of t is equal to limit s tends to 0, y of s, sy of s. The derivation, I am not deriving it like how it comes sy of s. That's a big derivation actually. You can just remember this formula. Is it clear now, or you wanted to ask something else, Ishan? Okay, cool. So if anybody has some doubt, uh, they can ask, or I will just close the meeting because I have another meeting to join. And it was really nice interacting. Like I genuinely feel good if somebody interacts and solves parallelly with me. Thank you guys. Like thank you very much for that. And I hope you learned something from this. Okay, sir, which textbook to refer for problem solving? For problem solving, actually, don't look into the problem solving right now. One good book which I referred that had very good concepts and problems as well was M. Gopal, Control System by M. Gopal, and another is Ogata. But Ogata is bit like, and another is Norman and Nice. But Norman and Nice is more towards the electronics. If you are from electronics background, if you are from electrical background, you can go for Ogata or M. Gopal. And if you are from electronics background, Norman and Nice, that's a very good book. And for concept, if you want very good concepts, then I would recommend you to the M. Gopal, or another book is there that is called Benjamin Kuo. Kuo or okay, yeah. So this is a very good conceptual book. You'll like, and my personal favorite is M. Gopal. Uh, it has some less problems, but the concepts are beautifully explained. And for problems, exactly for gate point of view, if you want to solve some problems, then I would suggest some gate books, because gate problems are little bit shorter, like you won't be getting bigger example, like the bigger problems, but for classroom studies, those are more important. Okay, thank you everyone. So I'll end this meeting right now. See you in next week. Actually, I don't know. I need to reconfirm. Next week we will be having a class or not, because next week is Independence Day. Uh, so you will be getting the mail regarding that. Okay. Thank you. See you. Good night.